Hello, we should now be live. It is 7:07 p.m., 7:08 p.m. Eastern Standard Time. Is it Standard Time now, actually? All right. Well, the last time we did an exam from the Massachusetts Institute of Technology, the entrance examination from 1869. That was yesterday. But today we'll continue with Algebra Can Be Fun. And there we go. We shall be doing the life of Diophantus. No, this isn't it. This is it right here. All right, we should have the right page. All right, I should find a way to actually make sure I am live. My channel, yeah, live. There we go. Should we open it? Should, we'll open it. All right, all right. We can see the chat. So this is famously one of the first algebra problems, and Diophantus is commonly known as the father of algebra. But so is oh no, Ibn. I don't know butcher the guy's name. Im Abdul Muhammad Im Muhammad Al Khwarazmi. He's also, I guess, Diophantus is the grandfather of algebra. Now, the algebra these days wasn't these x and these y's like we do now, like the x's. But in fact, it was about the unknown, about working with an unknown quantity. Doesn't mean we don't know the exact answer that we can't work. Oh, I got a big cup of water today. All right. So, very few facts about the life of the marvelous mathematician of ancient times, Diophantus, have come down to us. All that we know about him is taken from an inscription made on his tombstone in the form of a mathematical problem. Well, there are Diophantan equations, which are another thing, which we will not be working on today. So on his tombstone, yeah, usually it's on your tombstone's written what year you were born and what year you died. And with some simple arithmetic, we can find out the age of the person when they died. But Diophantus was like, that's too easy, too simple. Arithmetic? No, I'm gonna make them do some algebra, and I'm gonna tell my story as well. So this is the translated version. It's probably translated originally from, well, originally in ancient Greek, I would assume. But this book is Algebra Can Be Fun from written by Yakov Perelman. It was published in Russia, in the Soviet, no, Russia. It was Russia at that time. In when was it exactly published? Late 19th century, early 20th century. I think early 20th century. Let's find. Let's find out. This version was This version was the updated version, published in 1975 and then re-edited 1979. Let's see. Do we have any? It doesn't really say here. It doesn't say. It does I do know the age though. Let's see. Yakov Perelman was born in 1882 and died in 1942. Yes, during the siege of Stalingrad. When did he write his books though? Oh, it looks like later, early 20th century. Let's see. Physics for Entertainment, 1913. Let's see. Yeah, around that time. So let's say, yeah, around that time. All right. So this here was probably translated from Russian, but you can find modern versions, but it's always in a poetry form. So it's, yes, in those days actually, math equations, algorithms as Mr. That's where the Khwarazmi comes from. Algorithms. They were not get the steps. They were given in form of verse, and the steps to do like all of it sort of equation. It would be written with words. So first, we shall look at the ordinary language. In ordinary language, yeah, we'll read the whole thing first. We got time. Traveler, here rest the ashes of Diophantus. 'Tis a miracle that numbers can measure the length of his life. A sixth portion of it was a beautiful childhood. After a twelfth part in his life was over, down covered his chin. A seventh part he spent in childless wedlock. 5 years then passed, and he rejoiced in the birth of his first son, whom fate measured out a joyous and radiant life on this earth, but only half that of his father's. And in deep grief the old man ended his days on earth 4 years after losing his son. How many years did Diophantus live before death took him? All right. Well, that's a nice way of saying it. You got overtaken by death. Were we running away from death our whole lives, and it finally caught up? All right. Is that how we shall look at it? So let's see. Oh no, it gives the answer in the bottom. I should have covered that. I didn't notice that. Yes, yes, yes. The solution 84. But now we're looking in algebraic form. So what I'm gonna do here, I'm gonna use a lifeline to. So this is the birth of Diophantus at 0, and we have the end of his life. So we shall call that x. So all of this here is x. There we go. So the first part says a sixth of his portion was a beautiful childhood. So it's not going to be perfect around here. So this part here, in fact, we can color it. Shall we color it? Why not? That was a sixth of his life. So we know his whole life being x. A sixth of it would be x on 6. After a 12th part of his life was over, down covered his chin. Ooh, that means he started growing a beard. This should be half the size of that. So it's the green. So that was his early adulthood, let's say. Or his, well, not early adulthood, his teenage years, we'll say. Yeah, we should say that instead. The concept of teenagers, when I'm back in the day, didn't really exist back then. The idea of what a teenager, the, I mean, you were starting big enough to start working. So either you worked or you can continue your education if you were lucky enough. But most people in those days were not lucky enough. All right. So now he's a young adult. A seventh part he spent in childless wedlock. So he's a bachelor. So that is x on 7th. And there we go. Oh no, it's not going to be to scale. It's going to be pretty close though. All right. Now this next part is very important because now we're measuring this part of his life in actual numerical values and not just a part of an unknown. So 5 years then passed, and he rejoiced in the birth of his first son. Very. So that's about there right here. So this is a 5 right here. There we go. Oh wait, I forgot to color the yellow. Oh, there we go. All right. That's really sad. Whom fate measured out a joyous and radiant life on this earth, only half that of his father's. They say that is the greatest tragedy that a parent can go through. I wouldn't know. I have no children myself. Alright. So let's make that blue since it's sad. So this is half. Is it around half? Yeah, it's not bad. So that is half his life right there. While his son lived half the life. I should animate this. Should we draw a little baby? Wah, I'm a baby. There we go. A little baby. A little baby in the crib. That's my baby in the crib. Draw little arms. I don't know. Does that look like a baby in the crib? La la la. I guess that's a baby in the crib. What is this? This is like a. Alright, he's growing up, so he's a kid with his ball. Yeah, a kid with his. What would Diophantus play at with as a kid? Oh no, we should read the last part. In deep grief, the old man ended his days on earth. I should have made that. Well, we should make that black. There we go. Or gray at the very darkest, because we can't see much of black. There we go. 4 years after losing. So this four right here. Can we see it? Oh, we can't really see it. Oh, that's that four right there. So 4 years after the death of his son, Diophantus. Well, it says here ended his days. Ended his days. I was gonna say ended his life, but that doesn't sound good. Oh my gosh, you be careful. Maybe YouTube will be like, oh no. All right, he's a little kid. What would Diophantus play with as a kid? I don't know. A ball. There. Oh, a slingshot. Ah, like the ancient days. That's what they played with. All right, then this is his teenage years now. So he's a little taller. He's got a little beard. There we go. There we go. He's got a. Well, I guess. Well, he wasn't a warrior though, so I was gonna give him a. Well, what can we give him though? At the end of your teenage years, what would you be playing with? With a stick. There we go. He's got a stick now. People like sticks. All right. Now he's got a full beard. Oh yeah, he's a full man. We'll make him a little thicker also. He's growing, getting that body mass. Adult now. That beard doesn't. The full mass didn't work. The body mass did not work that well. It kind of covered his marvelous beard. All right, so he's still skinny. All right, what should we be playing with? What does he have? Oh yeah, he's gonna get married. Oh wait. Oh yeah, he got married. So we shall draw Mrs. Diophantus. There, she's got long hair, and there happily. There we go. And then I'm gonna do the other baby now. We're gonna draw the mini baby, and then we're gonna draw both parents again. So they're happy. You see, they're happy. They're happy with their new baby now. Well, we should put it right at next to 5. Oh, there we go. We got a nice big happy family then. That's the new baby son. Hey, there we go. All right. He's bigger than his father. All right. Oh, but unfortunately, he did not live that long. Well, I mean, maybe 42. So he's sad. Oh, he's crying. Shall we put his tombstone? Son. Oh no. And then finally, Diophantus himself. Should we draw death? Oh, shall I draw the specter of death? That's not too bad. We gotta have the sickle though. That will really tell. Oh no, we covered the 4, which in Chinese culture is a homonym of death. So that is not a lucky number. All right. So the animated part's done. That was fun. All right. So this is his whole life, but we know all of this is also equal to x. So let's look at all these parts right here. These are the parts that were the yeah, parts. They are parts of his whole life. He did not spend, well, I guess what's only 12 years? Oh yeah, well, the answer is 84, but that's what. So that's exactly 12. So we didn't in the problem it did not say, "Oh, his first 12 years was that of his beautiful childhood." It was a 6 of his life. So they're all parts of his whole life. So what we'll do, we'll add all these parts together. Oh no, I did x on 12 twice. It's x on 2 the second one. Oh, I did it again. Whoops, I did it again. All right, there we go. Now, well, we might as well do the work. We're gonna find now. Now we're gonna add these, add up all these fractions. Or, well, yes, exactly. At the end, what we're going to do, we're going to take out our x, and we're going to have 1 6 plus 1 12 plus 1 7 plus 1 half. And we're going to set this equal to this, well, and then plus the 5 and the 4. So these are the parts that we do know the numbers of. We do know it was 5 years after he got married. It's not part of his life, it's an actual numerical value. That his son was born, and then we do know that he passed away 4 years after his son passed away. So 5 plus 4, those two parts are equal to 9. Shall I write them both? Yeah, let's write them both. It's not going to hurt, but I'll put it like this in brackets, even though these brackets don't do nothing. And this was his whole life. So we know this part of his life, but this part also we can count the fraction of, and that's what we'll be doing. So in order to count that part, whoops, sorry about that, people, we need to count all the parts, yeah, the parts of that have the x variable in it, or the parts of his whole life. So should we go through this? Yeah, we got time. Why not? Shall we go through a little lesson on finding the PPCM? I think we could, no? All right. It's a little, I mean, at this level, this probably. So here, where I am in Canada, Quebec, Canada, this is probably a grade 8 problem. I would call it a grade 8 problem, but you can see it as easy. They don't usually see problems like this anymore, though. So, where it equals to it, it's a good. They're good problems, though. I do like them. I would use this as an introduction. I would maybe a grade 7 show it. Yeah, a grade 7 student should have no problem learning this, to be honest. All right, but enough of that. Let's continue with it. But let's do the PPCM. So we want to add together these fractions: 1 6 plus 1 12 plus 1 7 plus 1 half. The 7 is a bit annoying. So we got to find the PPCM of all of these numbers. But if we look at it, 6 is a multiple of 2. 2 times 3 equals to 6. And 6 is also, 12 is a multiple of 6. 6 times 2 is 12. So if we find the PPCM of 12 and 7, in that case, it will be the PPCM for the whole set: 6, 12, 7, and 2. So we can do the breakdown, but we should know that 12. So what I'm going to do, I'm going to do prime factorization. But 7 is a prime number, and 12 is not a multiple of 7. So the PPCM of all of these numbers would be 12 times 7. And we find that out, we get 84, excuse me. So, and then now we need to do 84 divided by 6. That gives 12. It doesn't give 12. What is 84 divided by 6? It's 14. I don't know why I said 12 for. All right, this gives 6. Oh yeah, the other one is 12. This gives 6 on 84. No, it gives 7 on 84. Why am I making silly mistakes for? All right, finally, this gives 12 on 84. And 1 half gives 42 on 84. But remember, this is all of x. And then we have our 9 here. And all of this equals. No, the microphone turned off. It does do that. Oh, we gotta shrink our beautiful picture. I'm running out of room. All right. So, now we can add all our numeraries together. 14 plus 7, 21. 33. 75. So we get 75 on 84x equals to 9 plus 9 equals to x. So now, instead of just solving the operation like we would, let's think about it. So these are the parts. 5 and 4 are the actual numbers that we don't have. We can reduce this fraction actually to, whoops, to 25 on 28. I hope we can see properly. Let me check if we can see on the stream properly though. Yes, you can. Oh no, you can't. Oh my god. Oh no, I shrunk it. Will you be able to see it? Is it getting shrunk? Oh no, you guys can't even see what I'm writing. I'm sorry about that, people. I gotta like. Oh no. Oh no. I gotta change the the OBS. Oh, there we go. Oh, everyone, let's make it a little bigger, actually. Who's on? I don't want to do it that big though. All right, now it should be better. All right. So, what does that mean? Well, that means this 9 years right here, it's equivalent to 3 on 25th, 28, 3 28ths of the life of Diophantus, because everything else is equivalent to 25 on 28. So what we do, we take the whole 1, let's say the whole life, x, minus 25 on 28x. So we'll get 3 on 28x. So now to solve for x, we get 9 times 28 divided by 3, which will give us the nice number of 84 years old, which is a ripe old age for, I guess, someone living in the BC era. So, but it was like that a lot, actually. Socrates lived to what? To his 80s as well? Yeah. Socrates there, he didn't die a natural death either. How old was Socrates when he passed away? Well, I would say passed away, but should I say murdered? 71 approximately. Oh, well, you see? Shall we find out how old all these ancient Greek philosophers were when they passed away? See, it's too big now. I can't see everything. I'm gonna make it smaller. A lot of jokes there, but I'll keep it to myself. Ah, there we go. We can see everything now. There we go. All right. So Diophantus lived to the age of 84 years old. So there we go. Now in the past, and before I worked on a similar problem, but the actual calculations for that problem, Newton's one, is much more. What is the word? What is very similar problem, but now it's about how much money a man has after he saved up and spent some. The same idea. The arithmetic is a bit more complicated, so I didn't want to actually necessarily go through this. All right. So this is one of the more famous problems there is. The life of Diophantus. It's classically known as a what? Oh yeah, it was 14, not 12. It was 14. So it's 14 here. He's 21 here. He's what? 28 here. He's what? 33? No, 28. Became a father at 38. What? Did I skip something? He didn't marry at 21. Wait, a sixth of his life was his beautiful childhood. Well, that's 14. It's right here. Oh, that's a mistake. Is there a mistake? He married at 28. No. No, he didn't get married at 21. He became, yeah, it was a childless wedlock. He got married at 28. Oh, yeah, he did lose son at 80. This doesn't make. Wait, is it 42? Should be 42, no. All right, his son lived to 42 years old. Oh, maybe I'm wrong. Oh my gosh. Wait, where's my 14, 7, oh 12. Oh yeah, 33. So 33. Oh no, no, no. Well, he did not get married at 31. He got married at 33. Yeah. All right. Then 38. Yeah, that's correct. And then he lost his son at 80 and he passed away at 84. There we go. So this is not right. He got married at 33. He became a man at 21. All right. So there we go. That's the life of Diophantus. The lifeline right there. Yeah. I should maybe make a more fancy animated version. That would be a bad idea, no? Alright. I might not view myself now. Did I stop my own view? Oh, how come I'm not showing up in my... Who's watching? Oh, did I get it? Alright, whatever. That's all good. Shall we continue? How long? 25 minutes. I did take my sweet time with this. Uh, let's open the... I didn't even open the book up, actually. Let's see. Let's plan our next thing. Oh, I got a French version also. Should we do this in French? Yes, I did mention this. I mean, Quebec, Canada. So, peut-être on peut faire la version en français aussi, n'est-ce pas? Mais maintenant, on va faire... Ah, the horse and the mule. Oh my gosh. Yeah, this is what horses and mules do when the humans aren't watching. And guess what? Guess what? We're gonna see. Just as usual. Just as usual. It is the mule that has to do all the work. These horses, man, all they do is look beautiful. I'm a beautiful horse. Look at me. But the mule, oh, working hard, hard-working mule, half horse, half donkey. Oh my God, all heart. No, I'm waiting for the thing to come back. That took a while. There's quite a delay, but it's not the end. That's about a what 15-second delay, I think. All right. The horse and the mule. Here is another problem that can be readily translated from words into algebraic symbols. A horse and a mule, both heavily loaded, were going side by side. The horse complained of its heavy load. "What are you complaining about?" replied the mule. "If I take one sack off my back, off no, sorry. If I take one sack off your back, my load will become twice as heavy as yours. But if you remove one sack from my back, your load will be the same as mine." All right. So, so now here they translate it really phrase by phrase. So we'll do that as well. Actually, did it here. If I take one sack off my load, so we shall say X is the mule's load. Oh, that's a lot of jokes there. Oh, and Y is the horse's load. That's it. That's it. The horse. Yeah. We know what they say about horses. It's got. Should we go? Should we go in this genre? Genre? Shall we start making package jokes? I think we'll leave it at that. All right. So, oh wait, the mule's load, the horse's load. There we go. All right. So, wait, is it the other way around? Yeah. If I take one sack off your back. Oh no, it's the other way around. Wait, let's reread it. No, off my load. If I take one sack. Oh, he takes. So X here. What is this? The way they wrote it. It's not done in the traditional way we do it these days. All right, you know what? Let's do it the traditional way. Not the traditional. Well, this is even more traditional, but so let X be what? Let X be the horse's load. No, we wrote mule's load before. Let's stick with mule's load. Ah, that happened again. I think I'm gonna leave this one on this live stream on. We'll see. So let X be the mule's load, and Y be the horse's load. Now, I'm gonna read this problem really carefully now. So no, we should do it the same as they did. I keep doing things like this. I'm so indecisive. I don't know what to put as my X and my Y. They're not independent dependent. You don't always have to have a dependent independent. You just want to find one result based on the other. In this case, we want to find, well, both the results. All right. So, the horse complained of its heavy load. So, what are you talking about? Replied the mule. So, if I take one sack off your back, that's the horse's load. And then he will take, all right? And then the donkey, not the donkey. Oh my gosh, I shouldn't call the mule that. He'll get off. Well, you shouldn't get offended though. Maybe a horse should get offended, but you're a mule. All right, and he'll take it. All right. So his load, the donkey's load now, will be twice as heavy. Yes. Oh wait, isn't it? Oh, this is the way they did. They did do it this way. So what does that mean? So we're gonna be really careful what we put the two. So so this is what is on the donkey right now, y plus 1. And this is what is on the horse right now, x minus 1. If the horse gives one of its loads to the donkey, so now it will be twice as heavy. So what we gotta do, we gotta multiply the horse's load by 2 in order for it to be equal to the mule's load, because the mule's load is twice as heavy, 2 times as much. All right, but now we have the other way around. The horse will take one of the donkey, the mule's load. What was it? There's a way. There's like a genetic thing about mules, and like whether their father or their mother was the donkey or something. I don't know. I forgot. They're not all sterile. I did read that somewhere. There's like, all right. So now the horses takes one of the donkey's loads. And there we go. So now we have two equations. Isn't that beautiful? So what we're gonna do here, we want to solve for x and y. You know, this is not a very, the numbers itself is not a very difficult problem. In fact, one could easily just use trial and error to find this answer. But we should not be using trial and error. What we shall be using is probably substitution. So what I'm gonna do, I'm gonna probably move this minus 1 to the other side. And there we go. Here, I'll write it like that. I'll highlight it. So I plus 1 on both sides. Why? Because what it will do, it'll make this minus 1 plus 1 equal to 0. And then I will have x plus 2 equals to y. And now I can replace my y with, in my first equation, shall we do another color? With 2x, or with x plus 2. These brackets we don't need, but I put them there anyways. And there we go. And now what we'll do, we're going to move, what I'm going to do, I'm going to move this minus 2 to the other side. How? By putting plus 2 on both sides. Why? Because, oh, whoops, I put plus 3. Well, we want to, our goal right now is to find out the value of x. That means isolate it on one side of the equation. When we do normal arithmetic problems, 3 times 4 plus 12 is equal to what? Well, this is our unknown. It's already nicely isolated for you, all by itself on one side of the equation. But here, it is not. So we got to move things around in order to find its value. All right. There's a plus 2 here. So we have 2x now. Minus 2 plus 2 is 0. You got to fill that hole. You fill the hole. So as I mentioned, now we have 2x on one side and x plus 5 on the other side. So what's our goal? We're going to move this x to the other side. We want all the x's isolated, segregated that way. So we're going to have, how are we going to do that? By minusing x on both sides of the equation. Whoops. Once again, why? Because we want to isolate it, so we want to move it. We'll say move it, but that's what we're doing. That's a plus. All right. So now we're going to have 2x minus x, and then we have, and now we have x minus x is 0. So, well, 2x minus x is 5, and now we have x equals to 5. Wait, that's the donkey's load, isn't it? Is it? Wait. So what's the mule's load? No, the mule's load is 7. No, that's fine. So the horse has 5. And the donkey, not the, why do I keep calling him a donkey? He's a mule. Half donkey, half horse. Wait, what were the ones who were half horse, half human? Centaurs? No, weren't they? No, minotaurs were cows. I think they were centaurs. Were they? Oh, there we go. Let's see. A centaur is a creature from Greek mythology with the upper body of a human and the lower body and legs of a horse. All right. I wonder if there's like a mule version, a donkey version. They're like little or something, you know? You know? Huh? Wouldn't that be neat? No? No? All right, all right. Well, then the mule, we'll know that x plus 2 is equal to y, so the mule would be 7. So now we can do the verification. Yes, if we minus 1 and add 1, the mule would have 6, and so would the horse, so they both be equal. But if the horse gives one of its loads to the mule, well, the horse would have 4, and the mule would have 8, therefore double. So that's a nice little verification. That's one nice thing about these types of problems, that you can always verify your answer at the end of the day. So I wanted to keep the same variable, so now we can just give the book solution right here. I should tell why people where the Algebra Can Be Fun is the book. You should be, when if you Google it, try to Google the word parallel along with it. Let's see if I just write Algebra Can Be Fun. Oh no, Internet Archive has it. That's nice. I know it's also available on the Gutenberg. Wow, that's a nice version. It's nicer than mine. No, it's the same, I think. It's also available on the Gutenberg project. Can we download it though? We can, but yes, it's in EPUB. That's it. That was the thing that was. Oh, PDF. Oh, PDF is available now. So on archive.org, search for Parallel Algebra Can Be Fun, and then there should be a PDF version. I'm trying to get it right now. I remember it was like when I got it, it was EPUB or something. I had to convert it, which was a slight annoyance, but not that much. Ooh, this will do for next time. But now rubles, 4 rubles in Russia. 4 brothers. 4 brothers. I'm gonna, you know what? I'm doing an accent. Four brothers have 45 rubles. If the money of the first is increased by 2 rubles, and the money of the second is decreased by 2 rubles, and the money of the third is doubled, and the money of the fourth is half, all of them would have the same amount of money. How much does each have? Alright, so we'll save this for next time. Alright, for next time. We'll leave you guys on a cliffhanger. And with that, I shall finish the mathematic portion of this live stream. Oh, it's downloading. Here, you know what? Let's see if I can do the on the fly. I don't want to make sure you guys don't see my personal information. I want to make sure everything is hidden. That's fine. Yeah, so they just, yeah, it looks like it's available. Algebra Can Be Fun on archive.org, a PDF version. It's taking quite a while to download though. It's only 8 megabytes, but that's all right. All right. Should we play some video games now? Yeah? No? No? Ah. Yeah, I'm gonna play some video games. Ah. I was gonna do, yeah, shall we? Let's do some math exams. Yeah, live. I was gonna do the math test in Yakuza like a dragon, but I already did that. Now, should we do that instead? Shall this be math and video game streaming? No. If I do video game streaming, I will do it. The microphone keeps turning off by itself. I don't know why it does that actually. I'm gonna find a reason. All right. Now there's 2 viewers now actually. That's nice. Well, I want to do this for next time. The 4 rubles problems. All right, let's play Yakuza. No? Oh, yeah, it's all set up. Let's do some of the questions. No? Wouldn't that be fun? Huh? Wouldn't that be fun? Let's see my live stream. Come on, chat. No one's chatting? No chats? Alright, so we'll continue this for next time. How long have I been going? Shall we do more? 39 minutes. Maybe we can do some more math. Well, we'll do this problem. How about that? We'll finish this up. No, we won't do this. We'll do this for next time. We'll do something else. Oh, since we're working on word problems, let's do the opposite. So, just to show you guys, let's see. I'm gonna make sure you don't see something. Make sure none of this is shown. Ah, that's fine. It's not the. Let's do a solve me puzzle. So this is another situation where we can use algebra to solve our unknowns. So these are very nice, actually. I'm gonna make sure none of my, no, it doesn't look like it. All right, now let me work on my OBS for a second, please. I need to add a source. I need to add a window capture, I think. Create new, and I need it to be. Oh, I'm running Yakuza right now. No, Brave. There we go. So I use the Brave browser. Uh, it's got an ad blocker in it. I quite like that. All right, here are the solve me puzzles. So, so I've been concentrating on word problems so far, but here's another situation that uses where we can use algebra to solve these puzzles. So I quite enjoy this. I do think this is a very good introduction to pre-algebra or something to do for pre-algebra. Because people will understand the concept of a scale. The left side must be balanced with the right side. So we'll do one easy example. Now, in these problems, you don't really actually need to do the algebra. You can just do it. Look, use your eyes and just follow the steps, and you'll be good to go. Oh, you know what we should do? We should do it this way. Yeah, we should do it directly on the thing. Oh, but I can't write now. That's the problem. I can't write over the screen. There is a way, though. I was checking it. There's a way to overlay over the screen. So I'll just do it the way I'm used to doing it. There is a way to overlay it over the screen, though. I did check it out, but I gotta install it one at a time. I gotta. Yeah, I'll put the camera on me soon, also, but we'll see. Not now. All right, what are you gonna do? What I gotta do? I gotta go to draw board. No, I gotta reshare my OCB. Let's get out of here. Window capture. Eh? Oh no, it's not working. Oh no, it is working. Wait. Oh no, I gotta put this in the back. Oh wait, hide it. Ah, there we go. I got it. I got it. There we go. All right. I think you guys see it now. Wait, let's check on the stream itself. No, I'm still at the. Still at the. Still at the what? Still at the browser. It should disappear. There we go. Yeah. All right. So this is like a scale, and this gives us the total mass of everything. And because it's a scale, we know the left side is equal to the right side. So now here we have 5 squares, and here we have 2 squares, and how many hearts? 5 hearts. So in order to find out, first we'll have to take 50 and divide it by 2. Because, there we go. So we know the total of the left-hand side, this will be the left side, is 25, and so will the total of the right-hand side. So now, to find the value of each square, we simply just have to divide 25 by 5. And we get 5 each. Alright. And then now what? So, since we know these are all 5, so the ones on the right-hand side would also be 5. So what does that mean? So we know all of this is 25. Since these two are 10, these 5 hearts have to be 15. So the value of the 5 hearts gotta be 15 divided by 5. And there we go. So that's a little simple one. Let's bump it up. This puzzle number 39. So let's add a 1 in front of that. 139. Ooh, oh, this will be much funner. Oh, 88 also. Nice number, eh? That's Now, I did mention before that 4 in Chinese language is a homonym of deaf. Well, it's not all negative. Well, it's negative only if you think of deaf as a negative thing. The deaf is not neither positive or negative. It is deaf. It is nothing. Okay, we're not going into that subject matter now. All right. Now, so should we give the whole page? Yeah. So in this the previous way we did it more arithmetically. We did not did steps. We did not actually use an unknown a symbol. Well, here there are symbols. The unknowns are the squares and the hearts. And we just solve it step by step like that. So we did not do algebra in the traditional sense. What happened there? But for the next problem, we will. Because it's a bit more complicated if you just try to do it that manner. Let me check what the stream sees. Just to be sure everything is working out well. Oh, only one watching now? Alright, that's fine. It says 2 concurrent viewers though on the thing. Who's right, who's wrong? Who knows? Maybe I gotta refresh it. No, I'm not doing that. Alright. So if we do like we did before, we take 88, we divide by 2, we get 44. So all of this is 44, all of that is 44. But then we got another division. So we'll take 44 and divide it by 2, and we get 22. But now we can't just find out the value of 1 because there is no branch, we'll call it, or thing that dangly line. There is none that has all the same shape. They're all different, so we can't just simply divide like we did before. But what we can do is we can see the relations between them. How much is one worth compared to the other? So how can we do that? So for example, let's look at these two right here. Because all we have right here are purple hexagon and what's the name of what's this color called again? What is that? Purple? That's not. I mean, it's like maroon. Is that maroon? I don't know if it's maroon, but the triangle. All right. We got hexagons and triangles here. Okay. All right. All right. We only have those two, so we want to know not exactly how much is one hexagon worth or how much is one triangle worth. It's how much they're worth compared to each other. Yes. So with that, what we'll do, we're going to do some canceling. So if I remove one hexagon on each side, well, since they both weigh the same, that means these 3 triangles will be worth 3 hexagons and 1 triangle. So I can also do that with a triangle. So now we have 2 triangles here and 3 hexagons. And we know they're both equal to each other. So we know 2 triangle equal to 2 hexagons. So now with that, what we can do, what can we do at this point? We can replace one with the other. So let's see, where would it be more convenient to do it? On the left side, on the right side? How many hexagons do we have? What we can do, we can do it for the total. It'll be a little simpler that way. We won't have to deal with fractions. So I have a total of 4 triangles here. Since 2 triangles is worth 3 hexagons, 4 triangles will be worth 6 hexagons. Right? So what we can do is replace these 4 triangles with 6 hexagons. Well, we also have the 5 we already had before. Well, that were not triangles, that did not get replaced. And we know all of that is worth, right here, 44. So we're going to add together all our hexagons. Hexagons are beautiful, aren't they? So 11 hexagons is worth 44. So to find out the value of 1 hexagon, we're going to divide by 11. 44 divided by 11, and we get 4. So now with that, we can find out the value of each triangle. So 3 times 4 is equal to 2 times the value of a triangle. 3 times 4 being 12. So to find out One triangle will be 12 divided by 2, 6. And there we go. So now the next step would be to find these green drops. So let's just fill in here. We get 4, we get 4, we get 6, we get 6. They are 20. So if all of this is 20, that means the two green drops have to be equal to 2. Therefore, one green drop is 1. So now we go on the other side. If one green drop is 1, and then we have 3 hearts here, well, that means the 3 hearts is worth 21. So that means 1 heart is worth 21 divided by 3 is 7. That's right. Was a love and it was a gas. These are orange hearts. And there we go. And that was so this one we had to use some algebraic expressions here to find out the values of each. And realize something. We had 4 unknowns and we got 4 different equations we could have wrote out. Well, maybe more actually. All right. And it will be a similar case when we do the 4 brothers problem. We have 4 different independent equations, or 5 actually. All right. Well, then we have more than enough to find it. All right. And we have 4 unknowns. So with that, I think we shall end it for now. What time is it? Yes. Unless I get a request to play. Wait, should we play some Yakuza? It is running in the background now. I think no, no, we won't do that. We won't do that. We'll keep it strictly educational for now. But we'll see how things goes. So, good grief, that was quite a long time actually. How long? 51 minutes. I think we shall end here. Well, we'll do this 4 brothers problem next time. And with that, I say goodbye until next time, everyone.